Hello, and welcome to The Sleepy Scientist. I'm glad you're here. Whether you've had a long day, a busy mind, or you simply love falling asleep to the sound of science, this video is made just for you. Tonight, we'll be gently gliding through the cosmos to uncover one of the strangest truths in physics. Why light, of all things, has a speed limit. But before we begin, I'd love to know, where in the world are you listening from? And what time is it where you are right now? Are you winding down under city lights, or nestled somewhere quiet and dark, perhaps with a cup of something warm? If you enjoy these sleepy explorations, I'd be so grateful if you gave the video a little like and tap that subscribe button. It helps more sleepy scientists like you find their way here, and it means I can keep making more of these soft starlit journeys for you. Now, I do hope this video isn't too interesting, though if it does accidentally keep you awake, at least you'll come away knowing a bit more about how our universe works. Not such a bad trade, really. So settle in, close your eyes if you like, and let's take a slow, thoughtful wander through the story of light, and why it's in such a hurry to get anywhere at all. Light is one of those things we all think we understand, until we actually try to explain it. You flip a switch, and there it is. It fills the room, lets you see your cat's judgmental stare, and makes your phone screen glow long after you swore you'd put it down. But what is it really? Is it a wave? A particle? A ghost? A cosmic courier with a very strict delivery schedule? The short answer is yes, and also sort of. Let's take a nice slow wander through what light actually is, because before we can understand why it has a speed limit, we first need to understand what's actually doing the speeding. First, let's talk about photons. They're the tiny packets that make up light. Imagine them as little messengers, zooming through the void at the fastest speed allowed by the universe. But these messengers are strange. They're not particles in the traditional sense, like marbles or peas. They don't have mass, they don't rest, and they definitely don't follow the usual rules. Now here's where it gets fun. Photons are also waves, but not waves like ocean waves or wavy hair. They're electromagnetic waves, vibrations of electric and magnetic fields that oscillate at right angles to each other and to the direction they're moving. Yes, it sounds like a physics yoga class, but the mental image is quite elegant. Two fields dancing through space together, locked in a perfect rhythm. These waves don't need a medium to travel through. That's important. Most waves, sound waves, water waves, even the wave you give your neighbour from across the fence, need something to move through. Sound needs air. Water waves need, well, water. But light? Light just goes. It travels through the vacuum of space without a problem. That's why we can see the sun, which is over 90 million miles away. Its light has travelled through the emptiness of space to reach us, without a single rest stop. And it doesn't just come in one flavour. The light we can see, what we call visible light, is only a tiny part of the electromagnetic spectrum. Imagine a piano that stretches for miles. Visible light is just a handful of keys in the middle. On one end of the spectrum we've got radio waves, long, lazy undulations that can stretch for miles. On the other end, we've got gamma rays, sharp, high-energy spikes that can pass through almost anything and are usually found in the company of exploding stars and nuclear reactions. In between, you've got microwaves, infrared, which your TV remote uses, ultraviolet, which gives you sunburns, and X-rays, which can see through your bones but somehow never find your missing socks. But despite all these differences, all these forms of light move at the same speed in a vacuum, roughly 299,792,458 meters per second. That's just under 300,000 kilometers every single second. A number so big it feels like nonsense. It's like saying, "How fast is that?" And the universe replies, "Yes." To put it in bedtime terms, if light were a runner, it could jog around the entire Earth more than 7 times in a single second. Not bad for something with no legs. But here's something else to keep in mind. Light doesn't always go that fast. In a vacuum, it's got a clear track and no traffic. But when it passes through something like water, glass, or even diamond, it slows down. Not because it's tired, but because it's interacting with the material's atoms. It's a bit like walking through a crowded room. You're still heading in the same direction, but there's a lot more bumping and weaving to do. That slowing down is what causes refraction. The bending of light when it moves from one material into another. That's why a straw looks bent in a glass of water, or why a diamond sparkles so brilliantly. It's all about how light's journey gets delayed, rerouted, and scattered. But here's the twist. Even though light slows down in these materials, individual photons still travel at the same speed between atomic interactions. They're just taking a more complicated path, like someone trying to speed walk through a dance floor full of enthusiastic uncles at a wedding. Now let's talk for a moment about colour. When we look at a rainbow, or a prism, or the weird oil slick in a puddle, what we're seeing is light split into its various wavelengths. Each colour of visible light has a different wavelength. Red is long and lazy, violet is short and twitchy. But all of them are still photons, still electromagnetic waves, just vibrating at different frequencies. Your eyes have special cells, cones, that are tuned to specific ranges of those wavelengths. That's how you see colour. It's not that the apple is red, it's that it's reflecting the wavelength we interpret as red while absorbing the rest. In a way, colour is just your brain's best guess based on which vibrations make it to your retinas. And as if all this weren't already wonderfully strange, light also has no rest mass. That means, unlike you or me or your slightly judgmental cat, it doesn't need energy to move. It always moves. It has no choice. If a photon were to stop, it wouldn't just be taking a break, it would cease to exist. It's motion, or nothing. All, or gone. That's not just poetic, it's physics. So we've got these massless packets of energy that behave like both waves and particles, that travel at a universal speed, that can interact with atoms, bend around corners and bounce off surfaces, all while delivering the very experience of sight and colour to conscious brains like ours. And that's just scratching the surface. But for tonight, let's hold on to this image. Light as a restless traveller, made of no substance but energy, never pausing, never sleeping, always tracing the outlines of everything we know. It shows us the stars, the faces we love, the pages of our favourite books. And it does all this while obeying one of the most curious rules in the universe, a speed it will never exceed and never fall below. Light isn't just what helps us see, it's how the universe whispers its story into our eyes. Let's take a gentle step back in time, long before satellites and lasers, before physicists had high-tech toys to measure the universe's secrets. Imagine a world lit only by fire and stars, where understanding something as elusive as light speed was not just difficult, it seemed almost absurd. For most of human history, people believed the light moved instantaneously. It was just there. You lit a candle, and the room lit up. The sun rose, and the world turned golden. No waiting, no delay. It seemed obvious. Why would anyone think otherwise? Even the ancient Greek philosopher Empedocles, one of the few to suggest that light might have a finite speed, wasn't taken very seriously. Aristotle, whose opinions had the unfortunate habit of sticking around for centuries, thought light was instantaneous, and that was that. Case closed, curiosity shelved. But then came Galileo. Now, Galileo was not one to accept things just because someone important said so. He liked to poke things, drop them off towers, and point telescopes at moons. And around the year 1638, he tried to measure the speed of light in what might be the most adorably optimistic experiment in history. The idea was simple. Galileo and his assistant each took a lantern, covered it, and stood on hilltops about a mile apart. Galileo would uncover his lantern, and as soon as his assistant saw the light, he would uncover his in return. Galileo would then measure the time between sending the signal and seeing the return flash. Now, even under the best of circumstances, this experiment was ambitious. The human reaction time alone is about 1/4 of a second. Light, meanwhile, takes less than 1/10,000th of a second to travel a mile. It's like trying to measure the speed of a bullet with a sundial. Still, you've got to admire the effort. Galileo, unsurprisingly, concluded that if light did have a finite speed, it was far too fast for him to measure. Which was true, but at least the question had been asked. Fast forward a few decades to a Danish astronomer named Ole Rømer, who in 1676 would accidentally stumble upon the answer by watching something quite far away, the moons of Jupiter. Rømer was tracking the orbit of Io, one of Jupiter's many moons, which zips around the gas giant like a cosmic clockwork. By carefully observing when Io disappeared behind Jupiter and when it reappeared, he noticed something odd. The timings weren't always the same. Sometimes Io appeared a little late, other times it was a bit early. At first glance this might seem like bad scheduling, but Rømer had a brilliant thought. What if it wasn't Io that was being inconsistent, but us? What if the delay was caused by the fact that Earth was sometimes farther away from Jupiter and the light from Io had farther to travel? And just like that, the idea of light having a measurable speed began to take real, scientific shape. From these timing discrepancies, Rømer estimated that it took light about 22 minutes to cross the diameter of Earth's orbit, a distance we now know to be about 186 million miles. That's not too shabby considering he didn't have access to accurate distances or modern clocks. His estimate wasn't perfect, but it was revolutionary. It told the world light takes time, not much, but enough to matter. Later, in the early 1800s, a physicist named Hippolyte Fizeau decided to try something more earthbound. His method involved a beam of light, a rotating toothed wheel, and a mirror placed several miles away. Here's how it worked. The beam of light passed through a gap between the teeth of the wheel, travelled to the distant mirror and bounced back. If the wheel was spinning slowly, the returning light would pass through the same gap and be visible. But if the wheel spun faster, the returning light would hit a tooth instead of a gap and be blocked. By adjusting the speed of the wheel, Fizeau could figure out the point at which the light beam was completely extinguished, meaning it had just enough time to travel to the mirror and back, while the wheel rotated half a tooth's width. Using the known distance and the wheel's speed, he calculated the speed of light to be about 193,000 miles per second. That's not far off the modern value, especially considering he was using mirrors, gears, and a whole lot of cleverness. Later still, another scientist named Léon Foucault refined the technique using rotating mirrors instead of toothed wheels, improving the precision significantly. He showed not only that light has a finite speed, but that it actually moves slower in water than in air, a critical clue that light interacts with materials in ways that affect its velocity. But perhaps the most iconic name in all of this is Albert Michelson. In the late 1800s, Michelson took Foucault's method and fine-tuned it to a level of accuracy that no one had achieved before. He used long tunnels, carefully aligned mirrors, and incredibly precise timing to produce results that stunned the scientific world. His efforts earned him the Nobel Prize in Physics in 1907, making him the first American to receive the honor. Not a bad reward for chasing beams of light around with mirrors. Today, we have even better tools: lasers, atomic clocks, satellites. We've defined the meter itself based on the speed of light. Since 1983, the meter has been officially described as the distance light travels in 1,299,792,458th of a second. In other words, we've flipped the equation. We no longer measure the speed of light. We use it as a standard to measure everything else. But it all started with people watching moons, spinning wheels, and wondering whether the universe might be slower than it looks. And maybe that's the quiet beauty of it. The speed of light isn't just a number, it's a story. A story of curious minds, imperfect tools, and elegant persistence. It's a tale told across centuries, from mountain tops and observatories and distant orbits. It's proof that even the fastest thing in the universe couldn't outrun human curiosity. So, now that we've met our speedy little photon friend and followed the long, curious journey to measure its pace, let's ask the question that really keeps physicists up at night. Why doesn't light just go faster? After all, it seems like a bit of an arbitrary number. Why 299,792,458 meters per second? Why not a nice round 300 million? Or 500 million? Or just infinite? Why does light, this ethereal, massless bundle of energy, have to obey a cosmic speed limit? To understand this, we need to take a calming stroll into one of the most elegant and mind-bending parts of physics: electromagnetism. More specifically, we're going to talk about a man named James Clerk Maxwell. In the 1860s, Maxwell took everything scientists knew about electricity and magnetism at the time. Think Benjamin Franklin's lightning rods and Michael Faraday's coils and magnets, and turned it into 4 beautiful mathematical equations. These are known, somewhat unimaginatively, as Maxwell's equations. They describe how electric and magnetic fields interact, change, and move. Now, you don't need to worry about the actual equations. No one's going to quiz you at bedtime. But here's the dreamy part. When Maxwell combined these equations, he discovered something extraordinary. They predicted a type of wave, an electromagnetic wave, that would naturally emerge whenever electric and magnetic fields wiggled in just the right way, and this wave would always travel at a specific speed. When he did the math, plugging in the known values for electric and magnetic constants, he got a number. That number, you guessed it, 299,792,458 meters per second. Maxwell was stunned. He'd found a number, a fundamental speed, buried deep within the laws of electricity and magnetism, and the kicker, that number matched the best available measurements for the speed of light. This wasn't just coincidence, it was a revelation. Light, Maxwell realized, was an electromagnetic wave, a self-propagating ripple of electric and magnetic energy, zooming through the void at a speed dictated not by chance, but by the very structure of the universe. Let that sink in. Light speed isn't just a habit. It's built into the equations that govern the fabric of reality. It's not like the universe randomly spun a dial and landed on that number. It's more like the universe had to work this way. If electric and magnetic fields exist, and they definitely do, then light must travel at this speed. So that's part of the answer. Light goes the speed it does because that's the only speed electromagnetic waves can travel in a vacuum. Anything faster or slower would break the laws as we understand them. But now let's go one step deeper. Why can't anything go faster than that? After all, in everyday life, we're used to speed being kind of optional. If your car goes 100 kilometers per hour, it can also go 110 if you're feeling daring. But with light, there's no upgrade, no speeding ticket, just a hard stop. To find out why, we need to call in someone you've probably heard of, Albert Einstein. In 1905, Einstein published his special theory of relativity, and with it, he changed everything. One of the key postulates of special relativity is this: the speed of light in a vacuum is the same for all observers, no matter how fast they're moving. That might sound tame, but it's actually bananas. Imagine you're on a train moving at 90% the speed of light. Very impractical, but excellent for thought experiments. You turn on a flashlight. You might expect that the light from your flashlight would appear to move faster for someone standing on the platform. After all, the train is already moving, and you've added the flashlight beam on top. But nope. Both you and the person on the platform would measure the speed of that light beam as exactly the same: 299,792,458 meters per second. Not a hair more, not a flicker less. To make that possible, reality has to bend itself around this rule. time slows down, lengths contract, mass increases. The universe changes the way it ticks to ensure that no one, no matter how fast they go, can ever observe light speeding up or slowing down. And if you, a brave astronaut, tried to accelerate to the speed of light, you'd run into a problem. As you get faster, your mass increases. Not in the eating too many cookies sense, but in the you're requiring more and more energy to go just a little bit faster sense. As you approach the speed of light, your mass trends toward infinity, and that means you would need infinite energy to reach it. Infinite energy is a pretty tall order, even for the most ambitious traveller, and so, no matter how hard you try, you can get close but never quite there. You can chase the light, but you'll never catch it. That's why the speed of light isn't just the speed of light. It's the cosmic speed limit, the upper bound on how fast information, energy, or anything with mass can travel through the universe. It's a barrier, a boundary, a fundamental part of space-time itself. And here's a peaceful thought. If the speed of light weren't limited, everything would fall apart. Causality, the idea that causes happen before effects, would break down. You could theoretically see an effect before the cause, or send information backwards in time. It would be chaos, time travel, paradoxes, and a serious headache for logic. Instead, the universe protects us from that kind of nonsense with this beautiful little speed cap. It keeps things ordered, predictable, calm. No matter what else changes, the speed of light stays the same. So the next time you watch a sunset or marvel at the stars overhead, remember, those beams of light didn't just happen to arrive. They followed a rule, one written into the very bones of physics. A rule that says, this far no farther. A limit, yes, but a limit that gives the universe structure, stability, and beauty. Light doesn't go faster because it can't. Not because it's weak or lazy, but because it's perfect exactly as it is, bound to a speed that keeps time flowing forward, keeps causality intact, and lets us understand the world in a way that would otherwise be impossible. And honestly, for something that zips across space at nearly 300,000 kilometers per second, I think that's a pretty graceful pace. Albert Einstein had a gift for flipping reality on its head and making it seem obvious in hindsight, like the universe had been whispering secrets all along, and he was just the first to actually listen. When he introduced his theory of special relativity in the year 1905, he didn't just tweak the rules of physics, he rewrote them. At the heart of his theory was a bold statement. The speed of light in a vacuum is constant. Not just generally constant, not pretty consistent if you're not moving too fast. Number absolutely constant. For everyone. Everywhere. Always. This might sound quaint if you're drifting off to sleep, but it breaks everything you think you know about motion and time. Let's say you're on a spaceship floating peacefully through the void. You're holding a flashlight. You turn it on. A beam of light shoots out in front of you at, say it with me, 299,792,458 meters per second. Now imagine someone else, your co-pilot perhaps, is flying past you in another spaceship at half the speed of light. From their perspective, you and your ship are whizzing by like a blur. But when they measure the speed of that same beam of light, they don't see it moving any faster or slower. They also measure it at exactly 299,792,458 meters per second. That's weird. Like deeply weird. In the everyday world, speeds add up. If you're walking on a moving sidewalk at the airport, your speed is your walking speed plus the speed of the moving belt. But with light, the sidewalk could be moving, the person could be moving, the flashlight could be moving, and the light speed stays the same for all of them. So what gives? Einstein's solution was beautifully unsettling. It's not the speed of light that changes, it's everything else. Time, space, the passage of moments, the size of things. All of it bends and stretches to preserve that one sacred number. Let's gently walk through the consequences. First, time dilation. This one's a favourite among physics students and science fiction writers alike. The faster you move, the slower time passes for you compared to someone at rest. Not just subjectively, it's a real, measurable effect. For example, let's say you're on a spaceship traveling at 90% the speed of light. To you, everything on board feels perfectly normal. You eat snacks, read a book, maybe wonder why you didn't pack more socks. But when you return to Earth, you might find that much more time has passed for everyone else than for you. Years, even decades. While you experienced a short trip, Earth aged without you. This isn't a theory that just lives in books. We've tested it. Particles called muons, which are created high in Earth's atmosphere by cosmic rays, decay in microseconds. But when they're moving near the speed of light, their internal clocks slow down and they last longer, long enough to reach the ground and be detected. Time actually stretches for them as they move. Next, length contraction. This is the strange twin of time dilation. When you travel at high speeds, objects in the direction of your motion appear shorter, not by optical illusion, but by physical reality. Your spaceship would literally measure shorter along its path of travel. Now, before you imagine yourself folding into an uncomfortable cube, know that this only becomes noticeable at speeds close to the speed of light. For everyday travel, cars, planes, or very enthusiastic joggers, the effect is so small it might as well not exist. But near light speed, the universe gets squishy. Then there's relativity of simultaneity, which sounds like a tongue twister but is actually a lovely bit of mental yoga. It means that two events which seem to happen at the same time for one person might not happen at the same time for another if they're moving relative to each other. Imagine a train moving very fast. In the middle of the train, a light bulb flashes. From the train passenger's point of view, the light reaches the front and back of the train at the same moment. But from someone standing on the platform, the light reaches the back of the train first, because the front of the train is moving away from the flash. Both observations are correct. Time and space are no longer universal. They're flexible, local, relative. All of this strangeness, time stretching, distances shrinking, simultaneity breaking down, it all happens to protect that constant speed of light. It's as if the universe looked at this one number and said, everything else can bend, but this must not break. It's a little like a cosmic contract. In exchange for allowing light to remain constant, the universe agrees to warp everything else around it. It's a delicate balancing act that keeps causality intact. Speaking of causality, here's a soothing thought. This cosmic speed limit is what protects our sense of before and after. Because light can only travel so fast, information can only travel so fast. That means you can't see an event before it happens, and you can't send a message into the past. Light's speed limit keeps the universe logical, predictable, tidy. Without it, things would get messy. You could, in theory, cause effects before their causes. You could receive a message before someone sent it. Paradoxes would pile up like socks in a teenager's bedroom. Instead, the universe gently says, no, let's not do that. Let's have order. Let's have a maximum speed, and let's make it sacred. And so, this is where Einstein's work shines brightest. He didn't just describe the speed of light as a limit. He showed that it's a cornerstone of reality, the cosmic scaffolding that holds up time and space. Today, GPS satellites rely on Einstein's equations to keep your phone from thinking you're in the middle of the ocean. Particle accelerators use them to guide subatomic particles around at astonishing speeds. Astronomers use them to decode the whispers of the cosmos from distant galaxies. All of it rests on this strange but constant truth. Light has a maximum speed, and that speed is the same for everyone. So the next time you see a sunbeam falling through your window, or a lighthouse flickering in the dark, take a moment to marvel at what that light represents. Not just energy, not just warmth, but the delicate geometry of space-time itself, a quiet contract written in the language of light. And no matter how fast you go, no matter how far you drift, it will always greet you at the same pace, unchanged, unwavering, and eternally on time. So far we've explored light itself, what it is, how we measured its speed, and why the universe insists on giving it such a precise and unbreakable limit. But now, let's gently pull back the camera and look at what this cosmic speed limit actually does to reality. Because once you realize that light can't go any faster than it already does, the implications are surprisingly far-reaching, and in many ways, quite beautiful. Let's start with something fundamental to how we understand the universe. Time. Not your kitchen clock kind of time, but the kind that ties together events, memories, and causality. Light's speed limit gives time a structure. It draws boundaries around what can influence what. It tells the universe you may only connect the dots if there's time for light to travel between them. This idea is what physicists call the light cone. It's not a snack or a lampshade. It's a way of mapping out what parts of space-time are connected by cause and effect. Imagine this. You're standing in a field and you light a match. That tiny spark sends out light in every direction. The furthest anything can be affected by that match, immediately or eventually, is limited by how far light can travel from that moment onward. If someone is standing very, very far away, say 100 light years, they won't even know the match was lit until 100 years later. Now flip it. Imagine you're standing in that same field, waiting for something to happen. The only events that could possibly influence you right now are the ones whose light has had time to reach you. That's your past light cone. Everything that could have possibly caused your present moment. The light cone isn't just a clever diagram. It's the border between possible and impossible. If something happens outside your light cone, it's not just too far away. It's too far away in time. No signal, no sound, no whisper from that event can reach you yet. It's as if it doesn't exist for you. Not until the light arrives. This idea shapes our entire understanding of the universe. It means there's no such thing as instant communication, no perfect synchrony across space, no omnipresent now. Instead, every moment is local. Every now is a bit different depending on where you are, and light speed is the rulebook that keeps it all consistent. Think about how this affects your view of the night sky. When you look up at the stars, you're not seeing them as they are. You're seeing them as they were. The light from the nearest star system, Alpha Centauri, takes more than 4 years to reach us. If something dramatic happened there last week, we won't know for several more years, and that's the nearby neighbourhood. Look further out, and the effect becomes even more dramatic. The light from the Andromeda Galaxy takes over 2 million years to arrive. You are seeing it as it looked when early humans were just starting to figure out how to make tools. Beyond that, we see light that left its galaxy billions of years ago, before our sun even existed. And yet it feels so present. The stars twinkle, the galaxies glow. They seem right there, but they're not. They're history, written in beams of light, travelling at their own patient pace. This delay is what allows astronomers to be time travellers of a sort. When they look into deep space, they're not just looking far, they're looking back. Every telescope is also a time machine, peering into epochs long gone. And all of this insight is possible because light doesn't move instantly. Its limit gives us access to the past. There's also something elegant about how this delay enforces causality. You can't influence something unless there's time for a signal to get there. That's not just a rule, it's a safeguard. It prevents paradoxes. It's the universe's way of saying, let's keep things logical. Without this speed limit, chaos would ensue. If you could send signals faster than light, you could, in theory, send a message to your past self. You could say, don't eat that suspicious burrito, and if you listened in time, you'd have no reason to send the message in the first place. That's the kind of logic loop that keeps theoretical physicists up at night, and not in a good way. But with the speed of light as a cap, those loops never happen. You can't outrun your own consequences. Events happen in order. The past stays behind you, the future ahead. It's not just the flow of time, it's the structure of time. And it affects more than distant galaxies or imaginary time machines. It's built into your day-to-day life. Consider communication. When you make a phone call or send a text message, you might not think about light speed. But if you're talking to someone on the other side of the planet, there's a very slight delay, tiny but measurable. The signal is travelling as electromagnetic waves, often bounced through satellites or fibre optic cables. These waves move at or near the speed of light, but Earth is big, and light, while fast, still takes time. Now think about spacecraft. When Mission Control sends a signal to a Mars rover, it can take anywhere from 4 to 20 minutes for the message to arrive, depending on where the two planets are in their orbits. That means if the rover stubs its robotic toe on a Martian rock, the scientists on Earth won't know until nearly half an hour later. There's no real-time remote control. The rover has to be autonomous, making decisions on its own because the speed of light says you're on your own out here. Even your favourite streaming service obeys this limit. Every pixel, every frame of your late-night documentary binge had to travel from some server, across cables and switches, all moving as pulses of light limited by the universe's built-in pace. It might sound like a constraint, but really it's a kind of harmony. The speed of light gives us a universe where effects follow causes, where the past is fixed and the future is waiting. It gives structure to space and time. It turns an endless, featureless void into a tapestry of ordered events. And while it might seem strange to think that the fastest thing in the universe is also the thing that slows down how quickly we can know something happened, that delay, those tiny moments of waiting, are what make the universe understandable. They give us distance, perspective, a little room to think, and maybe, just maybe, a little space to rest. Let's imagine, for a moment, that you're not the kind of person who takes no for an answer. You've heard all about this speed limit, this cosmic traffic rule etched into the laws of physics, and naturally your first question is, well, what if we just ignore it? Could anything ever go faster than light? It's a tempting thought. After all, human beings have a habit of pushing limits. We've broken the sound barrier, we've sent robots to Mars, we've built machines that can smash atoms apart. So, what's stopping us from finding some cosmic shortcut? Something that zips along faster than 299,792,458 meters per second. Let's start with a curious little idea from the theoretical physics basement: tachyons. These hypothetical particles were dreamed up as part of certain equations, and they come with an eyebrow-raising feature. They can only travel faster than light. In fact, they can't slow down enough to reach the speed of light. That's their limit in the other direction. Sounds exciting, right? A particle that naturally ignores the speed limit, zooming through the universe like a hyperactive squirrel on espresso. There's just one small problem. No one has ever found a tachyon. Not in a lab, not in deep space, not even lurking suspiciously in the gaps between equations. They're like a rumour in a small town, always mentioned, never seen. And even if tachyons did exist, they would cause more problems than they solve. If you could use them to send information, you could violate causality, meaning you could send a message into your own past. And if you've ever watched a time travel movie, you know how messy that can get. Grandparents disappear, timelines collapse, and everything starts to unravel. So, theoretical physicists mostly agree. Tachyons are fun to think about, but probably not real. They belong in the box labelled interesting but nope. But what about other fast things? Let's look at quantum entanglement, one of the spookiest phenomena in all of physics. When two particles are entangled, measuring one seems to instantly affect the other, no matter how far apart they are. You measure one here on Earth, and its twin, on the other side of the galaxy, reacts in perfect sync. It feels like a cosmic cheat code. Surely this is faster than light. Well, yes and no. The key point is that while entanglement correlations appear instantly, they don't transmit usable information. There's no way to control the outcome of the measurement on one particle, so there's no way to use it to send a message. It's like two people flipping identical coins across the universe and somehow always getting matching results. But neither one can use it to say, hello. Einstein himself was deeply bothered by this. He called it spooky action at a distance. But modern experiments have confirmed that entanglement is real, and that it doesn't allow for faster-than-light communication. The universe is spooky, yes, but still respectful of the speed limit. Then there's Cherenkov radiation, a bit of glowing weirdness that happens when a charged particle moves through a medium, like water. Faster than light can move through that same medium. Yes, you heard that right. Light doesn't always move at its full speed. In materials like glass, water, or plastic, it slows down a little due to interactions with atoms. So, if a particle moves faster than that reduced speed, it creates a kind of light shockwave, similar to a sonic boom. This is what causes the eerie blue glow you see in nuclear reactors submerged in water. It's not that anything is breaking the universal speed limit, just the local speed limit inside the material. Light in a vacuum still reigns supreme. No actual laws are broken, just bent a little in the pool. But what about going the extra mile? Could we build a warp drive, like in those classic science fiction shows? Could we bend space itself instead of just moving through it? Well, in theory, maybe. One idea, proposed in the 1990s by physicist Miguel Alcubierre, suggested that it might be possible to contract space in front of a spacecraft and expand it behind. This would let the ship ride a wave of warped space-time, technically never moving through space faster than light, but still arriving at its destination quicker than a beam of light could on its own. It's a clever workaround, but it comes with a few snags. First, it would require a substance with negative energy density, a kind of exotic matter that we have no evidence for and no real idea how to create. Second, even if you could build such a thing, the energy requirements would be, well, let's just say planet-sized. Some calculations suggest you'd need the mass energy of Jupiter just to move a grapefruit. So for now, warp drives remain firmly in the realm of imagination. Cool for storytelling, tricky for engineering. There's also the idea of wormholes, tunnels through space-time that could, in theory, connect two distant points instantly. Think of them as cosmic shortcuts, or space-folding bridges. Again, the math allows for them. But again, the problems stack up. Stability, exotic matter, time paradoxes. It's like trying to build a suspension bridge using soap bubbles and hope. And even if you could make one work, it wouldn't technically be faster than light travel. You'd just be taking a shorter path. The light still wins the marathon, but you've found a convenient side street. So, where does that leave us? Despite the clever ideas and curious exceptions, nothing with mass or information has ever been observed travelling faster than light. Every time we think we've found a loophole, the universe calmly steps in and closes it with a raised eyebrow and a chalkboard full of equations. And maybe that's not such a bad thing. The speed of light might seem like an irritating restriction, like a locked door at the edge of possibility. But in reality, it's more like a safety rail, keeping the universe from falling into paradox, chaos, and spaghetti timelines. It gives us structure, it gives us order, and it gives us a kind of cosmic serenity, knowing that no matter how weird things get, there are still boundaries that even the universe won't cross. So if you ever find yourself wishing you could beam across the stars or message your past self about tomorrow's weather, take comfort in the fact that light itself, swift, silent, and steady, is moving as fast as anything can. It's already leading the way, and perhaps that's enough. By now, you might be sensing a pattern. The speed of light isn't just some arbitrary number. It's a cosmic foundation stone, woven into the universe's very architecture. But what if it's telling us something even deeper than we realise? What if that mysterious, almost poetic number, 299,792,458 meters per second, isn't just a limit on speed, but a key to understanding space, time, and reality itself? Let's take a relaxed stroll into one of the more philosophical corners of physics. Don't worry, we're keeping it cozy. You can keep your slippers on. One of the most intriguing ideas in modern physics is that the speed of light is not just the pace of a photon, but a kind of conversion factor, a bridge between space and time. That number, let's just call it c for convenience, is what lets us translate distance into time and back again. It's like the universe's built-in translator. You've probably seen this in Einstein's famous equation, E equals mc squared. Here, the speed of light appears as a bridge between mass and energy. It tells us how much energy is locked up inside a certain amount of mass. But c also shows up all over relativity, in equations that describe time dilation, length contraction, and space-time curvature. The fact that it keeps popping up is no coincidence. It's a hint that c is more than just a speed. It's a kind of universal glue. Let's explore that with a simple, calming thought experiment. Imagine the universe is like a great woven fabric, made up of both space and time. Not two separate threads, but one single material, space-time. This concept, while sounding like a science fiction buzzword, is very real. In Einstein's theory, space and time aren't separate dimensions. They're interlinked, and they behave like one smooth, flexible thing. When you move through space, you're also moving through time. When you speed up, time slows down. When gravity pulls, it bends both space and time around it. But here's where the speed of light comes in. It's the conversion rate between space and time. Think of it like the exchange rate at a currency desk, but instead of euros and dollars, it's meters and seconds. This helps explain why you can measure distances in light years. That's not a measure of time, it's a measure of distance. 1 light year is how far light travels in 1 year. The fact that we can use a time-based unit to describe distance speaks to how deeply interwoven the two concepts are. So when we say nothing can go faster than light, we're also saying nothing can mess with the relationship between space and time. The speed of light defines that relationship. It's the stitching that holds the whole quilt of reality together. There's a certain calmness in that, because it means the universe has a kind of built-in consistency. No matter where you are, no matter how fast you're moving, c remains the same. It's a cosmic constant that makes equations work, keeps cause ahead of effect, and ensures that physics behaves itself even at the edges of black holes or the hearts of galaxies. In fact, physicists don't even treat c as just a speed anymore. In many natural units used in theoretical physics, they actually set the speed of light to 1, just the number 1. Not because they're lazy, but because it simplifies things. Once you do that, space and time can be treated on equal footing. Distances and durations can be measured in the same units. The equations get cleaner, more elegant. It's like the universe tidies itself up. This leads us to an even more curious idea. Maybe the universe isn't built for light to move, it's built around the speed of light itself. Think of it like this. When light travels, it doesn't experience time. From the perspective of a photon, the moment it is emitted and the moment it's absorbed happen at the same instant. There is no ticking clock inside a beam of light. Time, from light's point of view, simply doesn't pass. That's a wild idea. But it's backed up by relativity. The faster you go, the slower your clock ticks. For something moving at the speed of light, the ticking stops altogether. It exists only in motion, in the act of moving. It's never at rest. In fact, it can't be. And this brings us back to that poetic truth. Light is not just travelling through the universe. It defines the structure of the universe as it goes. The speed of light is not something that light chooses. It's something the universe insists upon. Even the way we define our basic units of measurement now revolves around this speed. Since the year 1983, the meter has been defined based on how far light travels in a certain amount of time. Specifically, 1 meter is the distance light travels in 1,299,792,458th of a second. That's not just poetic, that's precise. We've made the speed of light the ruler against which all rulers are measured. It's our measuring stick for both time and space, and perhaps that's the most grounding part of all this. In a universe that can seem vast and strange, filled with dark matter and quantum uncertainty, there is something beautifully fixed. The speed of light is a constant you can build your world around, because we quite literally do. So next time you see that little flicker from a candle, or the soft starlight filtering through your window, know this: you're witnessing more than just brightness. You're seeing a cosmic law in action, a message from the very geometry of space-time, a reminder that while the universe may be immense and mysterious, it is also quietly, elegantly consistent. Light doesn't just illuminate the world, it sets the rhythm of the cosmos. And perhaps, on a quiet night, as the photons from distant stars drift gently down onto your face, you can imagine the universe whispering in its own language, softly, steadily, at exactly 299,792,458 meters per second. By now we've seen how the speed of light isn't just some footnote in physics textbooks. It's the pulse of the cosmos, the stitch in the fabric of space and time, and the steady metronome that keeps reality in rhythm. But here's something that might surprise you. The speed of light isn't just out there, floating between galaxies or bouncing off distant stars. It's woven into your everyday life too. That's right. Even if you've never flown a spaceship or built a particle accelerator in your backyard, though if you have, hats off, you're still living in a world shaped, defined, and quietly orchestrated by the speed of light. Let's start with something familiar: your phone. Yes, that humble device you're probably listening to this on. Every time you tap the screen, stream a video, or send a sleepy emoji to a friend, you're harnessing the power of light, specifically light travelling through fibre optic cables. These slender strands of glass or plastic are the backbone of the internet. They stretch beneath oceans and continents, forming a global web that carries information at nearly the speed of a light. When you load a web page, you're not just waiting for a server to think about it. You're waiting for pulses of light, tiny flashes representing ones and zeros, to make their journey through these cables, bounce through routers, and arrive at your screen. And while the speed of light in fibre is slightly slower than in a vacuum, roughly 2/3 as fast, it's still astonishingly quick. We're talking about hundreds of thousands of kilometers per second. That's how your cat videos, weather updates, and bedtime playlists arrive with barely a pause. Now, those fibre optic cables aren't just moving data, they're also helping to keep time. You might be surprised to know that one of the technologies most reliant on the speed of light is the Global Positioning System, or GPS. When you use GPS to find your way to the nearest bakery, your device connects to at least 4 satellites orbiting Earth. Each of these satellites sends out a signal with a timestamp, down to the nanosecond. Your GPS receiver compares the arrival times of these signals to figure out your location. It's a bit like asking 4 friends how far they are from you, and then using that to triangulate your spot on a map. But here's the twist. For this system to work, we have to account for both special and general relativity, the very theories we've been gently strolling through. The satellites are moving quickly relative to Earth's surface, so their onboard clocks tick a little slower, thanks to special relativity. At the same time, they're higher up in Earth's gravitational field, which makes time tick a little faster for them, thanks to general relativity. The result? Without correcting for both of these effects, your GPS would be wrong by several kilometers every single day. Thanks to Einstein's insights and the rock-solid constancy of the speed of light, your GPS can tell you which turn to take to get to that croissant you've been craving. Let's zoom in even closer now, to your eyes. Vision itself is built on light's behaviour. When you look at the world, you're seeing photons bouncing off objects and entering your eye. These photons travel through the cornea and lens, get focused onto your retina, and trigger chemical changes in cells called rods and cones. Your brain then takes those electrical signals and reconstructs them into the vivid, colourful image of a tree, a sunset, or your oddly judgmental houseplant. All of this depends on how fast light can travel, how it bends through different materials, and how it interacts with the atoms in your retina. Even the fact that you see depth and motion relies on the delay, however small, between light reaching each eye and your brain comparing the inputs. And speaking of bending, Consider refraction, the way light slows down and changes direction when it enters a different material. This is what makes a straw look bent in a glass of water, or creates the shimmering effect you see on a hot road. It's also the principle behind eyeglasses, microscopes, telescopes, and camera lenses. Every time you snap a photo or read a book with glasses on, you're benefiting from our understanding of how light travels. Even the humble microwave oven owes its existence to electromagnetic waves. Microwaves are just a lower frequency form of light. They bounce around inside the oven, causing water molecules in your food to jiggle and heat up. Without the electromagnetic spectrum and our deep understanding of light's properties, reheating leftovers would be a far messier affair. Let's take a cozy step into the world of telecommunications. Your favourite radio station? That's just light too. Radio waves are part of the electromagnetic spectrum, just with longer wavelength than visible light. They travel at the same speed in a vacuum and allow your car to belt out music while you drive. Television broadcasts, Wi-Fi signals, Bluetooth connections, all of these are forms of electromagnetic radiation zipping through space, guided by the same rules that govern starlight and lasers. Now let's wander into medicine for a moment. X-rays, those ghostly images of your bones, are high-frequency electromagnetic waves. They pass through soft tissue but are absorbed by denser materials like bone. That contrast is what gives us the eerie, skeletal snapshot. And MRI machines, while they don't use light directly, rely on electromagnetic fields to create incredibly detailed images of the inside of your body. In short, light, or its extended family of electromagnetic waves, is quietly working behind the scenes in nearly every area of modern life. It's how we see, communicate, navigate, cook, stream, scan, and even study the stars. And speaking of stars, remember that everything we know about the universe beyond our own solar system has been delivered to us by light. Telescopes like the Hubble Space Telescope capture faint photons that have travelled for billions of years across the vacuum of space. These ancient beams carry encoded stories about galaxies, nebulae, black holes, and the early days of the cosmos. We decipher these stories by analysing the light's colour, intensity, and spectrum. A small shift in wavelength, a red shift, can tell us how fast a galaxy is moving away from us. A slight dip in brightness can hint at a planet passing in front of its star. A strange glow in the background might just be a whisper from the Big Bang itself. And it all works because light obeys the same rules everywhere. Whether it's a photon bouncing off your coffee mug or a ray of starlight from a galaxy 13 billion years away, it moves with the same unwavering speed. So the next time you open an app or look at the moon, take a moment to marvel at what's really happening. The quiet, graceful dance of photons, electromagnetic fields, and universal constants. The steady, tireless motion of light, racing around, through and within your world, all at the speed of 299,792,458 meters per second. Light isn't just a cosmic phenomenon. It's in your pocket, in your home, in your eyes. It's the quiet engine of the everyday. Take a moment, if you will, to imagine a single beam of light drifting through the vast emptiness of space. No planets, no stars, no gravity pulling at it. Just one solitary photon, gliding effortlessly through the vacuum, neither speeding up nor slowing down. It has no mass, no rest, and no need for fuel. It simply exists in motion, moving at the only speed it knows, 299,792,458 meters per second. That image, simple and serene, is more than just a poetic thought. It's a glimpse into the very fabric of the universe. Because this humble little beam of light is doing more than travelling. It's participating in the great cosmic symphony, a dance of information, energy and time that weaves the structure of everything we know. Let's begin with one of the most awe-inspiring pieces of light's legacy, the cosmic microwave background, or CMB. This isn't just a fancy name, it's the oldest light in the universe. It's been travelling, unbothered and undisturbed, for nearly 14 billion years. This faint uniform glow fills the universe and gently bathes everything in its presence. It's not the light from stars or galaxies, it's the cooled down remnant of the very moment the universe became transparent, about 380,000 years after the Big Bang, when things had finally cooled enough for atoms to form and photons to roam free. Before that, the universe was like a dense fog, opaque, chaotic, and hot. But once neutral hydrogen formed, light could move without constant interference, and so it did. It set off in all directions, a sea of ancient radiation now stretched by the expansion of the cosmos into soft microwave whispers. When scientists measure the CMB, they're literally catching photons that have been travelling since the dawn of time. These particles of light have never rested. They've crossed the universe just to gently land in a detector and say, here's what it was like back then. That's not just history, that's cosmic archaeology. But the story doesn't stop there, because light doesn't only tell us where we've been, it also binds everything we're experiencing right now. From the way stars shine to the way atoms behave, light is the silent participant in every process around us. Take photosynthesis, for example. It's the engine behind almost all life on Earth, and it starts when sunlight hits a leaf. Photons strike chlorophyll molecules, exciting electrons and triggering a cascade of reactions that eventually store energy in chemical bonds. Plants then use this energy to grow. Animals eat the plants, or they eat the animals that eat the plants, and so the chain of life continues. Without light there is no photosynthesis. Without photosynthesis there are no plants. Without plants, well, let's just say dinner would get a lot less interesting. In a very real sense, every meal you've ever eaten started with a photon from the sun. And it's not just plants that absorb light in interesting ways. Our very bodies are built to capture and respond to it. The human circadian rhythm, our internal clock, is deeply influenced by light. As sunlight changes through the day, it helps regulate our sleep, alertness, and even mood. A burst of morning light tells your brain to stop producing melatonin, the hormone that makes you sleepy. In the evening, fading light lets that melatonin rise again, nudging you toward rest. Even now, as you listen to this soft drift of ideas, your body is tracking the light around you, adjusting its rhythms, syncing to the world's subtle cues. But perhaps the most profound thing light does is connect. It connects not just eyes to objects or stars to telescopes, but moments to each other. It's how information travels. Every time we see something, every time we look across a room or across the sky, we're receiving messages, encoded in waves, shaped by space, and translated by our minds. Light is the language of the universe, and like any language, it has dialects, different wavelengths for different stories. Some tell us about the chemical composition of distant galaxies. Others warn us of gamma-ray bursts, the most energetic explosions in the universe. Some carry the warmth of infrared radiation from a newly formed star. Others paint rainbows across oil slicks and soap bubbles, revealing the hidden geometry of interference and refraction. This diversity is what makes light so powerful. It doesn't just show us what's there, it tells us how things work. A split beam passed through a prism reveals that white light is a symphony of colours. The light from a supernova reveals the fingerprints of heavy elements, forged in the violent furnace of a dying star. And the most remarkable part? We've learned to listen better. With radio telescopes, we hear the whispers of hydrogen clouds. With X-ray telescopes, we see the skeletons of galaxy clusters. With infrared instruments, we peer through dust to watch stars being born. We've even built gravitational wave detectors, tuned not to light, but to ripples in space-time itself, another cosmic messenger, complementing what photons have always told us. All of this paints a picture of a universe not as a cold, silent expanse, but as a place full of signals, full of stories, full of light. It reminds us that we're not separate from the cosmos, observing from afar. We're bathed in it, shaped by it, part of it. The atoms in your body were forged in stars that lit up billions of years ago. The light from those stars crossed interstellar space, touched gas clouds, seeded new solar systems. That same process created the carbon in your cells, the calcium in your bones, the iron in your blood. You are quite literally made of star stuff carried to you by light. And so, this restless traveller, this photon with no mass, no clock and no home, does more than move. It connects the ancient past to the present moment. It ties atoms to galaxies. It lets eyes see and minds understand. In a universe so vast and full of unknowns, light is a constant companion. Not just fast, not just fundamental, but familiar. It's the quiet presence that turns space into story, that fills the dark with meaning and that whispers across the emptiness, "I am still here." So tonight, as you settle in and let your thoughts drift with the stars, remember that even in the quiet, even in the dark, light is always on its way. And so, here we are, gently floating back to where we began. We set out to answer a simple question. Why does light have a speed limit? Along the way, we've wandered through fields of photons and danced with electromagnetic waves. We've listened to the whispers of the cosmos, seen time bend and space stretch, watched clocks slow down and stars speak in ancient beams. We've travelled through cables and galaxies, through your phone, your eyes, and the quiet glow of the microwave background. And the answer, in the end, is as elegant as it is profound. Light travels the way it does because the universe is built to let it, and to be shaped by it. Its speed is not just fast, it's fundamental. A cosmic rule that holds everything together, from the pulse of atoms to the stretch of galaxies. It isn't something that can be broken or outpaced, and perhaps that's a good thing. The speed of light gives us order, gives us time, gives us a way to understand. It gives us stories and sunsets and the warmth of starlight on a cold night. So maybe we don't need it to be faster. Maybe it's already perfect just the way it is. And now, as we bring this quiet journey to a close, let me ask you again, where in the world are you listening from tonight? And what time is it, right now, wherever you are? Are you curled up in bed with the stars outside your window, or sitting quietly on the other side of the world with morning light just beginning to rise? Wherever you are and whenever it is, thank you for spending this time with me. If this video helped you wind down or sparked a quiet wonder, I'd be truly grateful if you gave it a like and tapped subscribe. It helps others find their way here, to this calm little corner of curiosity. And if this video kept you awake, well, at least you might have learned something interesting while waiting for sleep to find you. Until next time, rest well, and may your dreams move at just the right speed.